Hi everyone, welcome to the lecture for week 4. This week we're going to be talking about risk aversion, and you'll see exactly what risk aversion means shortly. We'll also be looking at another decision theory, one that says that many risk-averse preferences can in fact be rational, even preferences that would be called irrational under the theories we've looked at so far, like expected value theory, expected utility theory. Here's the plan. So first, going back to the last week in our discussion of expected utility theory, you might wonder, how do I determine the correct utility function? Well, we'll have a look at two possible answers to that. And both of these answers allow for a particular sort of preference or pattern of preferences that we're going to call risk aversion. We'll look at what risk aversion is and how expected utility theory can accommodate it, how and when the theory says that risk aversion can be rational. And then we're going to look at two paradoxes for expected utility theory, two situations where the theory says that risk aversion is irrational. But these are also situations where intuitively you might think that it seems rational to be risk averse. It seems fine. So these paradoxes are a problem for expected utility theory. So we're also going to look at a new theory to replace it, risk-weighted expected utility theory, which, as the name suggests, allows for a lot more risk aversion. And we're also going to consider some points for and against this theory compared to the other theories that we've already looked at. Okay, so recall from last week, expected utility theory, here's the definition we had. Or an equivalent way to put the theory is just that preferences must satisfy completeness, transitivity, independence, and continuity. Thanks to the von Neumann-Morgenstern representation theorem, we know that that's equivalent to this statement of expected utility theory. But recall that the theory itself, stated this way, it says that there exists some utility function such that you're required to maximize the expected utility. But it doesn't say what the utility function is. So you might wonder, well, what's the correct one? Given, especially, that different utility functions often lead to different rankings of acts. So can we say that any particular utility function is correct? And if so, how would we do that? Well, one way we've kind of already seen, and that is that we can have further arguments that lead us to a particular utility function, such as the arguments we had for expected value theory. We had the long-run argument and the background uncertainty argument. And those effectively say that if you're following expected utility theory, you have to have a utility function that's linear in value. But perhaps you don't like expected value theory. You like having a bit more flexibility. For instance, as we'll see, you might be risk averse. Well, there are other ways that you can arrive at a particular utility function. So here's one. Reflective equilibrium. And what's reflective equilibrium? Well, it's a widely used method in various areas of normative philosophy, like ethics, for determining the correct normative theory. And lots of philosophers think it's a pretty good method. Some even call it the only rational game in town for the moral theorist, or more generally for the normative theorist, the decision theorist, for instance. And what does it involve? Well, it involves looking at lots of individual cases and considering your intuitions about what you ought to do in those cases. And lots of these intuitions about what you're permitted to do in particular cases, they might conflict. So for instance, if we're just thinking about ethics, you might have the intuition that when you go to the restaurant, to just order a burger made of beef is perfectly permissible. It just seems intuitively fine to you. But also when you think about other cases where your actions might cause suffering to animals, like torturing a puppy, that seems clearly impermissible. So these intuitions kind of seem in conflict. Also, in addition to your intuitions about individual cases, also consider what general normative principles seem justified or intuitive. So, for instance, alongside your intuitions about whether you're permitted to eat a burger and whether you're permitted to torture a puppy, you might also intuitively accept a general principle that, well, causing suffering to other conscious living beings is impermissible, at least when it's kind of easily avoidable. So again, we've got another kind of data point for determining the correct ethical view. And it seems to be in conflict with saying that you're permitted to eat the burger, assuming that eating the burger will then cause some cows some suffering. And where these judgments about individual cases conflict with one another, or they conflict with those general principles, then reflective equilibrium involves then adjusting them. And specifically, adjust them as little as possible such that we then have agreement among the principles and the intuitions, such that they're all in equilibrium. So, for instance, if our kind of ethical data points are your intuition about it being permissible to eat a burger, your intuition that it's impermissible to torture puppies, and the general principle that it's impermissible to unnecessarily cause suffering to other conscious living beings, maybe arguably the easiest way to make them all consistent is to adjust the first intuition about the case that it's permissible to go into the restaurant and eat the beef burger. If you just change that to, well, it's impermissible now, well then they all seem to be in agreement. They're all perfectly consistent. Maybe you could adjust the other two things instead, that, oh, well, sometimes it's fine to cause suffering to other living beings, or maybe it's fine to torture puppies, but you can adjust them in different ways. And reflective equilibrium is the process by which we adjust them as little as possible, such that we've then got a consistent normative view of what we're permitted to do. So we do so until we reach equilibrium, until they're all consistent. And then we've got a consistent set of recommendations of what's permissible to do, what we're required to do, and whatever we arrive at, you might think, well, that is the correct normative view for you to adopt, or perhaps the best justified normative view. And we can do something quite similar when we're trying to pick out a particular utility function. So suppose we already accept expected utility theory, perhaps the axioms of that theory from the V&M theorem, we count those as general normative principles of decision theory, but we still need to pin down a utility function. Well, we can just do reflective equilibrium. So we're now looking at individual cases and considering our intuitions about what we instrumentally ought to do. And let's assume that the V&M axioms are our general principles that are justified or intuitive. Well, where our intuitions about individual cases are going to conflict with one another or with the axioms, then we adjust a few of those. And we've seen lots of individual cases so far in the previous lectures where you might have had intuitions about what it's rational to do or what it's permissible to do or required to do instrumentally. And so you take all of those and you take other cases too, and you consider those intuitions, and you see which ones are consistent with the same utility function, and you adjust the ones that aren't. You remove the ones that aren't consistent. Or you try to adjust as few of them as possible such that you end up with a consistent utility function. So you keep doing this until you reach equilibrium, where they all fit with the same utility function, and that utility function that you've ended up with, that's the product of reflective equilibrium, so it's justified, or at least it's as well justified as your moral theory if you follow this process for picking a moral theory. So that's one way to arrive at a correct utility function, or to justify one utility function over others based on your individual intuitions about what we ought to do in such and such cases. That's one way. Here's another way. Instead, the decision maker who's actually facing a decision, they just look to their own attitudes, their own patterns of preferences about what they're permitted to do. So you, as a decision maker, might think that what you ought to do in situations of risk and uncertainty can be affected by three factors. What are those factors? One is your preferences over different outcomes, how strong your reasons are in favor of each outcome, how valuable the outcomes are, and so on. So your preferences. Second, the probabilities of those outcomes given each available act. And third, your attitudes towards different means of obtaining those outcomes. What do we mean by attitudes? Well, these are your own preferences concerning different sorts of risky acts, your sort of general patterns of preferences, your attitudes towards different broad classes of risky act. And to illustrate what I mean by this, by these sorts of attitudes, which are a little different to just regular old preferences, consider an example. So we've got risky bet versus safe bet. Risky bet is kind of riskier. It gives you probability a half of 2 lives saved, probability a half of no lives saved, safe bet, 1 life saved no matter what. And let's just assume for now that our value function, our preferences over outcomes are such that the more lives saved, the more preferred. And it might be that here, if you're the decision maker, you have a preference for safe bet over risky bet. And in general, you have preferences for safer acts like safe bet over riskier acts like risky bet. You have a general attitude of tending to prefer safer, less risky acts. So that's the sort of attitude we're talking about. It's not merely a preference in this individual case, but it's a pattern of preferences, kind of general attitude to features of acts. Okay. And if you have such a general attitude, that leads to this sort of verdict here that safe bet is preferred, then via this approach of just looking to the decision maker's own attitudes, the correct utility function to assign would then be one that accommodates this preference, this attitude that safer bets tend to be preferred to riskier bets. So in general, the correct utility function is determined by the decision maker's own attitudes of this sort. And yes, it's not merely their preferences over acts, but their preferences over general kinds of risky act, for example, based on how risky the act is, that determines the utility function. So that was two ways of determining the correct utility function, or of justifying a particular utility function as being the correct one to use in a particular decision. Those ways were, first, reflective equilibrium, second, looking to the decision maker's own attitudes. And the key difference between these two, the first gives us one correct utility function that applies for all decision makers. So even though you, as an individual, are thinking about your own intuitions, you're trying to determine what's the correct normative theory, or more specifically, what's the correct utility function to use for everyone based on your intuitions. Whereas the second one, going to the decision maker's own attitudes, that can easily give us different utility functions for all the different decision makers. Because what an individual decision maker ought to do is then determined by their own attitudes. So it may vary between people in different decisions. And another thing to note about each of these is that for reflective equilibrium, it is, as a method, pretty well justified, or at least it's pretty popular among philosophers. So it's widely considered a good way of arriving at correct normative views. Whereas the second one, looking to the decision maker's own attitudes, it's not so well justified. It's certainly not a widely used methodology in, for instance, ethics or aesthetics, these other areas. But nonetheless, it does seem to be a common approach, a common view that this is correct among decision theorists. So that's maybe something worth objecting to, or you might think it's fine. But anyway, if we're following either of these two methods, either looking at your intuitions about which acts are preferable to which others, or you as the decision maker looking to your own preferences, your own attitudes towards different sorts of acts. Either way, the answers we end up with, the utility functions we arrive at, will depend on the attitudes that someone has towards different sorts of actions, how we feel about different sorts of actions. In particular, our attitudes towards risk. And different people and different decision makers do often have different attitudes towards risk. So this is a general sort of preference for acts involving more or less risk. For instance, again, risky bet versus safe bet. You may prefer safe bet over risky bet, and more generally prefer acts that are less risky, even when their expected value is the same, like here, because you have this general attitude towards the riskiness of acts that you tend to prefer bets that are safer, acts that are safer. If so, we would say that you're risk averse. That's what this term means. That's what we mean by risk aversion. Having a general preference for acts that are less risky where their expected value is the same. So expected value being equal, we want less risk. In this case, more specifically, we're not simply risk averse, we're risk averse in the number of lives saved. Or you could say risk averse in value if you think that what's valuable is number of lives being saved. Because being risk averse generally, we're risk averse in different quantities, different amounts of stuff. Now, it's important to note that by risk averse in philosophy and in this unit, we don't mean a sort of common usage of the term that you might sometimes hear. So it doesn't just mean preferring some less risky options, because sometimes there are less risky options that also have higher expected value or are just uncontroversially preferred to other options, other acts. For example, in this case, we've got risky bet and then we've got safe bet where we've increased the number of lives saved. And you might notice here that safe bet dominates. It both state-wise dominates and stochastically dominates the risky bet. So sure, this safe bet here, it's less risky than risky bet, but it's clearly better. It's clearly strictly preferred. You don't need to be risk averse in this general sense of having a preference for less risk. Whatever your attitude towards risk, you're probably going to prefer the safe bet here, given that it simply state-wise dominates the alternative. You don't need to be risk averse to prefer it. And in everyday life or everyday conversation, if someone had to choose between these two acts, and then you ask them about it afterwards, why did you choose that thing? They might say, well, I was just a bit risk averse. I was averse to this risk of saving no lives, so I had to choose safe bet +1. Well, yeah, that makes sense in English, and people might often say that sort of thing, but that's not what we mean by risk aversion here. It's not merely preferring an act that happens to be less risky, it's preferring the act that's less risky because it's less risky. Okay. So here's from the picture on the intro slide, we have a kind of risk-averse decision maker, a risk-averse agent, someone who doesn't want to stand too close to the edge of the cliff. And risk aversion, more precisely, is going to mean preferring acts with less variance in their outcomes, variance in a certain quantity, where the expected amount of that quantity remains equal. So that may sound a little confusing. What do we mean? Informally, that means how big the differences between outcomes are in whatever quantity we're talking about, for instance, number of lives saved. So if you're risk averse in the number of lives saved, then you will prefer acts where there's not so many differences, not such big differences between the number of lives that will be saved by that act. And there is a technical mathematical definition of variance, capturing and measuring exactly how much the overall differences between outcomes might be, but we really won't need that for this course. Even more roughly, variance is how spread out the values of the different outcomes are. So just as an example, again, we've got risky bet and safe bet from before. So here, the numbers of lives that you might save via risky bet, two lives or 0 lives, 2 and 0 are more spread out, those two numbers, than 1 and 1. 1 and 1 are very close together because they're the same number. They're less spread out, and so we would say they have less variance, or safe bet has less variance in the number of lives that would then be saved. And by this definition, if you're risk averse in the number of lives saved, then in this case, you will prefer safe bet over risky bet, because after all, they result in the same number of lives saved in expectation. They have the same expected number of lives saved. So given that they have the same expected number of lives saved, if you're risk averse in the number of lives saved, you'll strictly prefer safe bet over risky bet. Same expected amount of the quantity, but safe bet has less variance. The numbers are less spread out. Another way to think of risk as variance, or how spread out the numbers are, which may or may not be helpful, is this. So same case, same bits of text, but we can draw a graph of the different numbers of lives saved, or the different kind of values that would result from each act, and the probability of each of those values. And we would have what's called a probability distribution over number of lives saved. So such distributions are here. So in blue, this one in the middle is safe bet. Because the number of lives saved, 1, we have probability 1 of that many lives saved. So that's the probability. Meanwhile, for risky bet, possible number of lives saved, possible values are 2 and 0, and we have probability 1/2 of each of those. So these go up to 1/2, both there and there. And you might notice that this graph of safe bet, it's very concentrated. The probability mass is not at all spread out. It's very concentrated. Whereas the probability mass, we call it, of risky bet is much more spread out. It has much more variance. And this is what it looks like to have more variance when we graph the probability distribution. If that way of looking at it doesn't make a whole lot of sense or doesn't help, but you've got the idea that, yes, these numbers, 2 and 0, are more spread out than 1 and 1, then that's fine. You don't have to worry about understanding probability distributions graphed in this way. It's just here in case it's helpful. Okay, back to risk aversion. So here's the definition that we just had. It's preferring acts with less variance in their outcomes, variance in a certain quantity, where their expected amount of that quantity is equal. Or put simply, to prefer acts that are less risky, where their expected value is the same. And it's worth noting that risk aversion, at least as I'm defining it here, it's always in a particular quantity. So if you're risk averse, you have to be risk averse with respect to some quantity. So for example, you could be risk averse with respect to the number of lives saved, or you could be risk averse with respect to the number of dollars that you win in a lottery, or in moral value, or whatever it is. And it's worth noting that being risk averse with respect to one such quantity doesn't necessarily mean being risk averse with respect to another. So I'm almost certain that all of you are going to be risk averse with respect to money that you win, or gain through profit. But perhaps you're not all risk averse with respect to number of lives saved, or amount of happiness, or something like that. So Here's an example in terms of money. So you might be risk averse with respect to money here. You might prefer to win $500,000 for sure than to flip a coin and maybe win $1 million, maybe win nothing. You might prefer the safe bet here. And given that the expected amount of money is the same in either act, if you prefer safe bet, that would indicate that you're risk averse in amount of money. But if we think about these outcomes not in terms of how much money you win, but in terms of how much happiness the outcome brings you, maybe this preference no longer indicates risk aversion. So the amounts of happiness, if we just pretend that we can put some sorts of units on happiness and measure it in a precise way, it's not clear that we can, but whatever, then the amounts of happiness that correspond to, say, $1 million might be 150, whereas the happiness corresponding to 500,000 might be 100. So it's more than half as much as getting the $1 million and gaining no happiness for winning nothing. Well then, the expected amount of happiness you get from safe bet in money is higher than the expected amount of happiness you get from risky bet in money. So, preferring safe bet, it no longer indicates risk aversion with respect to your own happiness. Even though it does indicate risk aversion with respect to money. So you can be risk averse in one thing without being risk averse in another thing. Okay. But for the most part in this unit, we're going to focus on risk aversion with respect to value, whatever sort of value our normative theory gives us. Maybe it's happiness, maybe it's lives saved, maybe it's years of healthy life that you gain for yourself. Doesn't matter. It's value. And if we simply say risk aversion or risk averse without specifying what quantity we're talking about, just assume that we're talking about value, whatever value is. Okay, so that's what we mean by risk aversion. And note that risk aversion isn't the only risk attitude you could have, the only sort of attitude you could have towards the phenomenon of risk. So we had the girl over here who's staying away from the cliff and wants to stay safe. We also have the boy on the edge of the cliff who, doesn't really worry so much about the risk. So he has a different risk attitude. So yes, risk aversion isn't the only risk attitude you could have. There's also risk seeking, we would call it, and that is to prefer acts that are riskier, to like to live dangerously, or more precisely, it's to prefer acts with more variance in their outcomes, more variance with respect to some quantity, whether it's value or whatever, at least where their expected amount of that quantity is equal. We also have risk neutrality, and that is to be neutral, to not care about the riskiness of an act, just the expected amount of whatever quantity we're talking about. So this is, more precisely, to be indifferent between acts of different variance so long as they result in the same expected amount of whatever the quantity is. So if the quantity is value from our normative theory, then being risk neutral just means to follow expected value theory. And another term we could use, as long as you're not risk neutral, is to say that you're risk sensitive. So that is to not be risk neutral, but instead at least sometimes prefer acts that are more or less risky, at least where their expected value is the same. So for instance, to be risk seeking or to be risk averse, that would count as being risk sensitive. But also, you need not always be risk averse or always be risk seeking in order to be risk sensitive. You could be some weird combination of them. For example, you could have a risk averse preference when comparing certain acts and a risk seeking preference when comparing certain other acts, and that would count as still risk sensitivity. To be risk sensitive is simply to not be risk neutral. But in this unit, almost entirely, we're not going to worry about risk-seeking preferences or more general risk-sensitive preferences. We're going to focus on risk aversion versus risk neutrality. Because it turns out most people tend to be either risk-averse or risk neutral. Few people tend to be risk-seeking, except maybe habitual gamblers, and also in moral decision-making, most people's intuitions are either in favor of risk neutrality or in favor of risk aversion, not these other things. So we'll be focusing largely on risk aversion. And risk aversion is something that we can accommodate to some extent within expected utility theory. If risk aversion is the sort of attitude that you have towards risk, whether you're the decision maker or someone looking to your intuitions to figure out the right utility function, if you're risk averse, that will lead to a certain sort of utility function. And the theory can, to some extent, handle such an attitude. And to see how that might go under expected utility theory, consider this case again and suppose that you prefer safe bet to risky bet. And You prefer it not because you disagree with the value function that's linear in lives saved. You do agree that, yes, 2 lives saved is basically twice as good as 1 life saved. But instead, you prefer safe bet because you're risk averse in value, in number of lives saved. Well, we can accommodate this verdict within expected utility theory, for instance, with a utility function like this that says the utility of no lives saved is 0, the utility of 1 life saved is 1, but the utility of 2 lives saved, it's not 2, it's slightly lower, it's 1.5, for instance. And then the expected utility of safe bet will be 1, because the average of 1 and 1 is 1, and the expected utility of risky bet will be the average of 0 and 1.5, so 0.75, which is lower than expected utility of safe bet, so expected utility theory would then say safe bet is strictly preferred. So we've accommodated a risk-averse verdict.
Nice.
Hopefully that sounds very familiar from cases we considered last week and how the theory might go. So yes, we can accommodate risk aversion within expected utility theory, but how do we do so? Well, to do this in general, for any given quantity like numbers of lives saved or what have you, we will need to adopt a utility function that has a particular shape, a shape like this. It's concave, or more precisely strictly concave, but we can just call it concave. It's concave with respect to that quantity. So we might have value or number of lives saved on the horizontal axis, and the utility of having that many lives saved on the vertical axis, and it kind of curves downwards. Or the fancier way to say that is that it's concave. So a concave function is one that, like this one, increases by less and less the more of the quantity you already have. So the more value you have, the slower it goes up. It increases less and less for each additional unit of value. So it's a function that gets less and less steep for larger numbers of, say, lives saved, or whatever quantity we're talking about. Another way to put it is that its slope, how quickly it rises, its slope is strictly decreasing. And one thing that you can say if you want to, and you'll often hear people say, is that with a utility function like this, value, or lives saved, have diminishing marginal utility. So when a utility function is concave with respect to some quantity, we can say that that quantity has diminishing marginal utility. And in case it seems kind of mysterious how having a utility function that gets less and less steep leads to risk-averse verdicts, consider, again, the same case of risky bet and safe bet. Here it is. Now, assuming that the value function is just linear in lives saved, the values of these different outcomes are 0, 1, and 2. And if we were taking the expected value of risky bet, we'd be taking the average of 2 and 1, so we'd be taking the number that's halfway between them, which is 1. So the average of 0 and 2 is here. But then consider what the utilities of these different outcomes are. So here are the utilities with this utility function, and we're supposing that those are the numbers from before, which would involve having a function with this kind of shape. And now notice that the utility of 1 life saved is much closer to the utility of 1.5, the utility of 2 lives saved, because we've kind of, by getting less and less steep, we're kind of compressing the function more and more as we go along. But when we're taking the expected utility, we're taking the average of these utilities, so the expected utility of risky bet is going to be the average of 0 and 1.5, halfway between these numbers, which is going to be down here, which is going to be lower than 1, the expected utility of saving 1 life for sure. So by having our function be concave, having it be kind of compressed more and more as we get higher, we're pushing down the averages of acts that give you some probability of something down here and something down here. We're going to push that average down by pushing down this part of the utility function. Hopefully that makes sense. So basically, on expected utility theory, to be risk-averse just means to have a utility function like this, one that's concave. Okay, so that's how expected utility theory can accommodate risk-averse preferences, risk-averse verdicts, risk-averse risk attitudes. And you might think, that's great. Okay, this theory that I've learnt about, it can accommodate the sorts of preferences that I have. For instance, if you intuitively prefer safe bet over risky bet, you might think, great, the theory can accommodate that, and my utility function looks like this. But if you yourself are risk-averse and you have preferences like this, maybe hold on a moment, not so fast, because expected utility theory, it can't accommodate all sorts of risk aversion, even all sorts of risk aversion that we might intuitively think are rational. And there are a couple of moderately famous cases where it seems to say things that rule out risk aversion.
Oh my God.
So here is one such case. You're going to enter a lottery, you're going to buy a certain sort of ticket, and a number is going to be drawn from 100 balls. And here are two tickets that you could buy. The first one just gives you 100 million for sure, and the second one is slightly risky. So, for the first 90 balls, yes, you'll still get $100 million. For the next 10 balls, 90 to 99, you'll win 500 million. Okay, great, even better. But then for the 100th ball, you would then win nothing. Now, which of these acts do you think is preferable? Which do you intuitively think you're required to take or would be rational for you to take? Well, you might think, $100 million, if I had that much money, I would be set for life.
Very nice.
And here we're talking about, what's preferable for you, for your own well-being. Forget about morality for the moment. But if you had $100 million, hopefully that would be enough to give you quite a nice life, and any money-related problems you might have would be completely resolved. And 500 million, well, that would be even better. You could get a slightly fancier yacht. If you're going to spend your money on a yacht, you could get a slightly fancier mansion. Maybe you could even afford to live near UWA campus, who knows. But $500 million would be great, but it wouldn't be that much better for you. And winning nothing, well, obviously that would not be so great. But you might think intuitively here, yeah, it's rational to go for the $100 million. You might intuitively prefer it. You're guaranteed to make your life pretty great, and you don't want to take this risk of winning nothing. You'd like to guarantee that you're going to have a great life. At least you want to guarantee that you're going to have enough money to have a great life. Who knows how it will actually go. Okay, so that was one preference that you might think is perfectly rational. Now here's another pair of tickets that you could buy in a different lottery that's somewhat less generous. Now the first ticket that you could buy, this one that we'll call a chance of $100 million, well, for the first 90 numbers that might be drawn, you win nothing, but then with the remaining 11, you win $100 million. So you have a probability 11 out of 100 of winning 100 million. And then the second one, which is descriptively called almost the same chance of 500 million. So the first 89 numbers, you win nothing. The next 10 numbers, probability 10%, you'll win $500 million, so that's great. And the remaining one number, probability 1%, you would win nothing. Now, you might think here, well, either way, I'm very unlikely to win anything. And both of these acts have almost the same probability of winning something really good. So this one has probability 11% of winning 100 million. This has probability 10% of winning 500 million. And 500 million is, it's quite a lot better than 100 million. Even though 100 million is great, 500 million would be fantastic. And it's kind of worth trading off this 1% chance for a much higher potential payout. At least you might think that's rational to have such a preference. So you might intuitively prefer this one, almost the same chance of 500 million, over a just slightly higher chance of 100 million. Okay. Hopefully, if you have that preference, then great. If you don't have that preference, just kind of imagine you do, or consider whether you think it would be at least rational to have that preference. Okay. So now consider all four of those acts listed out together, and notice something that these two have in common with these two. They're exactly the same, except we've changed what happens in this first state over here. So you may have intuitively preferred this first one, and then down here you might have intuitively preferred the second one. But here's a question for you. Is that actually possible under expected utility theory? If so, I want you to figure out what's a utility function that would actually give you those verdicts. Or, if these preferences aren't possible under expected utility theory, why isn't it possible? I'll give you a little time to think about that. Okay, time's up. The answer is no, it's not possible to have these two preferences. Apologies to anyone who tried to find a utility function that actually made it possible. There is no such utility function that would work here that would give you both preferences. And the reason for that is that having both these preferences would violate independence. Now, maybe that's not super obvious because it doesn't follow immediately from the definition of independence, but notice what happens if we just ignore those states. This is the same as this. So however we prefer this act here, just between those two possible outcomes, to this other act, we have to have the same preference once we introduce this extra state over here. And likewise, our preference between them has to be the same even when we introduce these things here. And that means, by transitivity, that whatever we prefer between these two acts, once we're considering all three states, has to be the same preference that we'd have between these two acts, considering all three states. So independence with an extra step, independence plus transitivity, tells us that $100 million for sure can only be strictly preferred to this thing if a chance of 100 million is strictly preferred to almost the same chance of 500 million. So you can't both prefer this one and prefer this one. Not by expected utility theory, because that would violate independence. Yes, so expected utility theory can't give both of these verdicts. There is no utility function that would say this. And you might be somewhat surprised by that. You might be somewhat annoyed by that if you liked the sound of expected utility theory and you happen to have these preferences. You might think, well, it's perfectly rational to care here about the fact that if I were to take slightly risky, this second act here, there is some chance of getting absolutely nothing. The worst case scenario here is much worse than the worst case scenario here. And it's rational to try to avoid the worst case scenario. So yeah, go for 100 million for sure. Whereas in the second one, sure, this is the worst case scenario, but you have the same worst case scenario in the other act. Either way, there's a really high chance that you're going to win nothing. So given that you're probably going to lose anyway, you might as well go for the just ever so slightly riskier act, gambling for 500 million rather than gambling for only 100 million. That might seem rational. Plenty of people have thought, yeah, that is rational. And because so many people have thought intuitively that, yeah, it's rational to have these two preferences, this is often referred to as a paradox. It's called the Allais paradox. It comes from a Nobel Prize-winning economist called Maurice Allais, who's French, so I probably mispronounced that. But yes, this is seen by many as a problem for expected utility theory, because it seems to be rational to be risk-averse in this sort of way, to be risk-averse such that you would prefer this first act over the second one, but not risk-averse in the way that expected utility theory captures, that says, therefore, risk aversion must also lead you to prefer a chance of 100 million over a chance of 500 million. Okay. Now, another sort of case where expected utility theory can't allow for risk aversion in a way that seems kind of rational, is in a case like this. So we've taken the risky bet case from before, and I've just swapped out 2 lives for 3 lives. So we'll call this risky bet for 3 lives. And let's just suppose that you prefer these two acts equally. Admittedly, safe bet has lower expected value, a lower expected number of lives saved, but if you're a bit risk averse, you might nonetheless think, well, it's equally preferred because, I don't like the fact that there's so much risk in the risky bet, even though, the expected number of lives saved is higher. Okay, so suppose you think these are equally preferred. If you are risk averse, but you don't find them equally preferred with these numbers, adjust the numbers a little bit, just so you get something that's equally preferred, and that's fine. We can use any such case where the expected values are different, but you nonetheless think that they're equally preferred. So it might be this case, might be a slightly different one. Okay, you might prefer these equally. You might also prefer them equally if we add something to every single outcome. So this is the same as before, and then we just add 100 lives to every outcome. We've made them all more preferable in exactly the same way by adding 100 lives. And you might think, well, still, the only difference between these acts, or between any of these outcomes, is not the 100 lives, that's the same. It's still just 3 extra lives saved, 0 extra lives saved, 1 extra life saved, 1 extra life saved. So because we thought they were equally preferable before, we also think they're equally preferable now. Or at least intuitively, you might think they have to be equally preferable. And it doesn't just have to be 100 lives, it could be any number of lives added. You might still intuitively think, yeah, it's got to be equally preferable. Okay, so that was adding a bit of extra value. We can also scale up the amount of value, the amount of number of lives saved in each outcome like this. So same case as before, and then multiply them. Multiply by 10. So now it's 3 times 10 lives saved, 0, 1 times 10, so 30, 0, 10. And you might think, well, this is the same pattern as before, and because I intuitively thought that, 3 lives, a coin flip between 3 lives saved and 0 lives saved is equally preferred to 1 life saved for sure, then, a coin flip between 30 lives saved and 0 lives saved is equally preferred to 10 lives saved. And likewise for any other number, it doesn't have to be 10, whatever number you want. So you might intuitively think that all 3 of these pairs of acts have to be equally preferred. Or equivalently, that if you think a coin flip to save 3 lives is equally preferred to 1 life saved for sure, then that would stay the same if we sweetened every outcome by a certain amount, or we scaled up the number from 3 to whatever, but we scale up all the outcomes by the same amount. Okay. But, fun fact, expected utility theory doesn't allow this. There's no utility function by which expected utility theory would give these 3 verdicts in general. And this finding comes from a 1988 paper by someone called Bengt Hansen, but unfortunately this result, this paradox, it isn't quite as famous as the Allais paradox, which you'll hear about in every decision theory textbook you read. If you want, you can call this Hansen's paradox. I think it's more of a paradox than the Allais paradox, but anyway, just terminology. Also, now the reason for this is maybe more mysterious than for the Allais paradox. For the Allais paradox, we can just say, yeah, independence implies this, and it's moderately clear. Whereas with this, there's no single axiom of EU theory that obviously shows that we can't get all these preferences at once. But nonetheless, you can't do it. If anyone's curious about kind of why this isn't possible, I would encourage you to draw a graph of a concave utility function, such that which you need in order to get this preference, and then try and get all of these verdicts at once. Try and use that same utility function to also say that once we shift the values, the number of lives across, that the shape has to be the same. We end up with the same kind of averages of the utilities. And likewise, when you kind of stretch the numbers out, so you go from 0 and 3, you go to 0 and 30, or whatever. Try and draw such a function and see if you can get the same verdict in all 3 of these cases. And you will fail, I suspect. But it's helpful to draw it out and see for yourself. Okay. So to summarize what we've just seen, expected utility theory rules out some preferences over acts, preferences that may seem intuitively appealing or may seem rational to us. And specifically, those preferences in both of those cases were preferences that we would endorse if we're risk averse. So expected utility theory is ruling out what seems like a rational sort of risk aversion. Now, one philosopher who's thought that this is a particularly serious problem for expected utility theory is Lara Buchak. And in one of the readings for this week, the introduction to her excellent book on this subject, she says this. So by expected utility theory, if a rational decision maker does not like taking risks, there's only one way that can be accounted for. It must be attributed to the fact that the utility values they assign to outcomes are lower than their face values. So by this, in our terminology, she's saying the utility we assign to outcomes is lower than their value according to our normative theory. However, intuitively, being averse to taking risks, it's not a matter of disvaluing different outcomes or weighing different outcomes differently. We still, value each outcome the same amount. We still have the same preferences over outcomes. But rather, being averse to the risk of an act is caring about this property of the act as a whole, this general property of how risky the act is. So she says, rather, it's a matter of treating what will happen in the worst case scenarios as more important to one's choices than what will happen in the best case scenarios. More generally, she says, it's a matter of being sensitive to global properties of gambles, properties of the act overall, nothing about each individual outcome taken by itself. So what does it mean to be sensitive to a global property of a gamble? It's being sensitive not just to what happens in each particular outcome, but to what the gamble looks like as a whole. So global properties include especially what the worst case and best case scenarios are, and also the extent to which the values of a gamble are spread out, how much variance there is, which, as we saw before, that is a big part of the definition of risk aversion. And she claims that in practice, many decision makers, many of us, do care more about what happens in the worst case scenarios. We are sensitive to global properties of gambles in a way that, on the face of it, expected utility theory cannot capture. And it's not just on the face of it. In specific examples, like the Allais paradox and the Hansen paradox, where caring especially about the worst case outcomes, caring especially about what the worst case scenario, if you take a particular act is, that leads you to having preferences that seem to deviate from expected utility theory, preferences that expected utility theory can't capture. So if we think it's rational to be risk averse in these ways, the ways that we saw in those examples, and also the way she describes of caring about the worst case scenario more, well then we must reject expected utility theory because it can't accommodate those preferences. Thankfully, Buchak has an alternative. She has a further theory that we could consider as well. But before I give you the big scary definition of it, the blue box definition, we'll sort of go through it and just illustrate roughly how the theory is going to work. So recall first how expected utility theory accommodates risk-averse preferences with a concave utility function. So it deviates from expected value theory by effectively modifying the value of the outcomes, replacing value with utility, and utility kind of downweights how good we treat certain outcomes are. It downweights the very best outcomes to kind of count for less and less utility. Now, Buchak's approach deviates from expected value theory in another way. That is, it effectively modifies the probabilities of each outcome in a given act. So we're kind of applying the modification to a different part of the expected value equation. So here's our simple example again of risky bet versus safe bet. And the very rough strategy that Buchak is suggesting is that, take the expected value of risky bet, but when you're doing so, give this worst case scenario of no lives saved, give that extra weight, effectively give it more probability, and give this best case scenario less weight, give it less probability. Because if you're risk averse, at least in her view, being risk averse is best captured by being more worried, being more concerned about what the worst case scenario will be, which does kind of equate to the definition we saw of caring about how spread out the outcomes are, caring about whether something is the worst case scenario and how much worse it is. Okay, so that's the very rough strategy, which we're now going to see less roughly. Okay, so her theory is going to have us compare acts by something that she calls the risk-weighted expected utility. So as the name suggests, we're kind of deviating from expected utility and expected value by caring about risk, adding some extra weighting. And unsurprisingly, the theory is called risk-weighted expected utility theory, which is, the names are starting to become a bit of a mouthful, so you can call this REU theory for short, if you would prefer. Now, to see how it works, consider how we would calculate the expected value of risky bet again. And we're assuming here that the value function is just linear in lives saved. V of x lives saved equals x. Now, the expected value is this, which we would then fill in, and it would look like this. Or if we were to rearrange these numbers a little bit, but still say the same thing, we could put it this way. So this is in terms of the worst case value 0 plus a half times 2, or 2 minus 0. And that won't mean much yet, but we can kind of, in general, rearrange this equation for expected value. So here it is again, the expected value of risky bet. And we could rearrange it like this, both in this case and in general, if there are only two states.
And the worst case outcome has value 0.
So the value of the worst case outcome, which was here the value of no lives saved, plus the probability of getting the other outcome, multiplied by the value of that other outcome. So the value of this plus the probability of this times the value of this. Okay. Which is also just what I was doing here. Whoop. Now, if we rearranged the equation for expected value like this, then we've got this probability by itself, ready to be messed around with. And via Bouchak's theory, we're going to weight this probability differently. This is the probability of getting something better, and we're going to give less weight to that, effectively more weight to this. So here it is in red, because we're going to mess with it. If we wanted to give more weight to the worst case outcome and less weight to the best case outcome, we could just replace this probability with a smaller probability, a smaller number. And that's going to be the basic strategy of the theory. So we could use a different function. So R, it's what Bouchak calls the risk function, and she uses that to capture risk attitudes, risk aversion, and so on. And this is a function of probability. So we apply a function to this probability, and it makes the probability smaller. For instance, we could change it from a half to a quarter using this risk function. So instead of going 0 plus a half times 2, we're going 0 plus a quarter times 2, and that ends up being a half. That's the kind of risk-weighted expected utility of this act using this particular risk function. And a half is less than the expected value of safe bet, which is 1. So then we would get the answer that safe bet is strictly preferred. Now, if we want to apply this sort of strategy to other cases that are slightly less simple, then we need this equation to also be slightly less simple. So one thing that helped us here was that the value of this outcome here is 0. And that actually makes a difference to whether or not we can write the equation this way. In general, if the value here is not 0, then we need to write it in a slightly different way. So slightly more generally, if we want to get this sort of weighted average of the outcomes values where we've kind of applied extra weight to the worst case outcomes and less weight to the best case outcomes, and we have any act with 2 possible outcomes, we can do it like this. So here is a slightly modified version of risky bet. So now we've got 3 lives saved or 1 life saved. And what we're going to call the risk-weighted expected utility is going to end up being this. So again, we start with the value of the worst case outcome, and then we add to that probability of the other outcome multiplied by the difference in value between 3 lives saved and 1 life saved, the difference between these 2 outcomes. And then we also kind of weight this probability here by an R function, a risk function R. And in this case, if we just plug in the numbers, we've got value 1 plus, and this is going to be the probability a half, that's the probability of getting the better outcome. And then the difference between the 2 values is 3 minus 1. And then we also use this risk function R, so we're going to weight that probability a little differently. So for instance, it could be that the risk function replaces a probability of a half with a probability of a quarter. It's kind of weighting it down. And then it's going to be 1 plus a quarter times 2, or 1.5. And again, that is less than the expected value of this act. So this act has expected value 2, but the risk-weighted expected utility here is giving us a lower number. So this would be equivalent to saving 1.5 lives, for sure, whatever that means. Okay, so again, just like before, we're getting a sort of weighted average of these 2 values, but we're giving extra weight to the worst case outcome, or equivalently, less weight to the best case outcome. And we're doing that by kind of rearranging the equation like this, such that it's the value of the worst case outcome plus a probability times a difference in value now, rather than just a value. But then we're applying some weight. We're weighting the probability a bit differently using this risk function. That's what's happening. Okay. So you might think, okay, that's great. We've managed to put a number on this act. We've managed to give it a risk-weighted expected utility, which would suggest that it's not quite as good as what its expected value would suggest. But why on earth can we do that? Where has this equation come from? It's a very reasonable thing to wonder. Well, so we can actually get this equation kind of out of expected value theory and then just doing something to the probabilities like this. So the expected value of this act is going to be the probability of this outcome times the value of this outcome plus the probability of this outcome times the value of that outcome. Okay, hopefully that's familiar. And we can just rearrange this, do a little bit of algebra. We can rewrite the probability of 1 life saved as the probability of 1 minus 3 lives saved. Because remember, the probability of all the states added up is going to be 1 by the kind of Kolmogorov axioms of probability. So we can replace this term here with 1 minus probability of 3 lives saved times the value of 1 life saved. And we leave the rest the same. Okay? And then we can rearrange this. So we've got the value of one life saved times 1 plus the value of one life saved times, or minus the value of one life saved times that. So we've spread that out. And then we can kind of regroup these things. So we've got the probability of 3 lives saved twice. We can kind of collect these terms here, this value and this value, behind the probability of 3 lives saved. So just more rearranging, we've got the value of 1 life saved plus this probability times this value minus this value, which was over here. Okay? So I've colored them in red and blue in case that's helpful. Red was the first half. That's the probability and the value of 1 life saved. And the second part is the value and the probability of 3 lives saved. And then as we rearrange them, this is where those terms are moving around to. Okay. And they end up like this. And this is the equation that we had just before of, with this 2-outcome case, of the value of the worst case outcome plus the probability of the other outcome times the value of the other outcome minus the, so the difference between the values here. It's just the same as that, except here we've applied this risk function R to the probability. So there's only one probability left in the equation, and we're going to weight that differently. So you can think of risk-weighted expected utilities as expected values rearranged and then weighting the probability a little differently. Okay? Now, if this bit of maths makes no sense at all, I do recommend kind of pausing the lecture for a little bit and just thinking through each of these steps and kind of reassuring yourself that, yep, this here, this line is the same as the first line. They mean the same things. Each of these steps is kind of a legitimate step to take. And then Buchak's suggestion is, once we've done this rearrangement, we notice that expected value can be rearranged like this, then we've got the probability by itself, we do something to the probability, and thereby we give more weight to the worst case outcome and less weight to the best case outcome. Okay. Now, I've kept it simple so far with just 2 outcomes, 2 states, and that does kind of simplify this equation. If we had more states, we would have a lot more terms here to add together and rearrange and blah, blah, blah. But this strategy does work in general. We can do this sort of rearrangement, and it'll be more than just one probability. If we have 3 states, then it'll be the value of the worst case outcome plus the probability of the rest of the outcomes multiplied by this difference, plus another probability of the very best outcome multiplied by another difference in values. But this is the underlying idea of how the risk-weighted expected utility relates to, say, the expected utility or the expected value. There's a rearrangement going on, and then we're weighting the probabilities. Okay. Now, slightly more generally, when we've got more than 2 states, still we want a risk-weighted expected utility. We want a kind of weighted average of the outcome's values with more weight to the worst case outcome. And yes, more than 2 possible outcomes. The general method will look like this. So here's a case with more than 2 outcomes, and here's the procedure I want you to follow when in the exam you're asked to give the risk-weighted expected utility of an act like this, which we've called dicey bet. So first thing to do, identify the lowest possible value, the worst possible outcome, and call it V1. Okay? Or later on, more generally, we'll be calling it U1 because we're dealing with utility, not value. But for now, just worry about value. Okay. This is the worst one, the least preferred one, call it V1. And here that value is 1. V1 equals 1. And then we list the rest of the values from least preferred to most preferred, from worst to best. So V2 is the second worst, V3 is the third worst, and so on until you have Vn is the very best outcome. Here we just have V1, V2, V3, and they equal 1, 2, and 3. Okay. So we've got our list, and then for each of these values, we need to ask, what's the probability that this act here will result in that much value or more? And the or more is going to be really important. In fact, it's very easy to make mistakes when calculating risk-weighted expected utilities because it's easy to forget which probability we're talking about. So the probability that the dicey bet results in a value at least as great as V2, this value or greater, that probability is 2/3 because it's the probability of getting 2 or 3. So that's 2/3. And the probability of getting value v3 or greater, that's 1/3, because the only way that can happen is this state here, probability 1/3. Okay, and that's all the information we need to fill out the general equation for risk-weighted expected utility. What is that equation? It looks like this. So I realize this is going to look a bit intimidating, but it is, at its core, doing the same thing that we just saw before. So don't worry about this sigma notation for now, just look at the other terms. We have a V1. We have a V1, which we found, V1 equals 1. We're also going to have some probabilities that the value of the act is at least as great as some VI, and VI is going to be V2 or V3. What's the probability that it's at least as great as V2? It's 2/3. And the probability that it's at least as great as V3, that's 1/3. So we have those probabilities. We also can get these differences. So this will be V2 minus V1 and V3 minus V2. And since we know what V1, V2, and V3 are, we'll be able to calculate those differences. Just to reassure you that, yes, we have all the information we need. It's not as complicated as it looks. But I do need to explain what this sigma notation means now, because it's a little different to what we saw before. Okay, so a quick maths note. So far, we've been using sigma notation that looks like this. So we've got a big sigma symbol, and then below we've got something like S is an element of big S. And this means that for each element, little s, of the set big S, we add up one of these expressions from the right. So f of S1 plus f of S2, where S1, S2, and so on are the s's that are in the set big S. Okay? Now, we'll also be using a bit of sigma notation that looks like this, like in the definition of risk-weighted expected utility. And this is a bit different. Now we have something below and above. Specifically below we have some variable, some letter like I, and we're saying I equals 1, and then at the top we have n. And this means that we'll be doing the same thing, but we'll be adding up terms like this, 1 for every value of I from 1 to n, from I equals 1 to I equals n. So we add up f of 1 for I equals 1, plus f of 2, I equals 2, plus so on until we get to f of n, that's when I equals n. So we're not using a set, we're using a list of different values that I can have. Whole numbers from 1 up to n, or whatever number we start with. We could start from 2, doesn't matter. Okay, now that we know what this means, we can go back to that scary looking equation and to the case from earlier. Here's the equation, and for now we'll just focus on I equals 2, so the first of these terms that we're adding up, and there is a second one, but we'll just leave it off for now. And we've got V1 out the front, and that's plus, for the first term of this, we fill in I equals 2. So VI becomes V2, VI again becomes V2, VI minus 1 becomes 1. 2 minus 1 is 1. Okay, now what are these different bits? In fact, we have all of them from before. So this is the value of the worst case outcome. It's 1. This over here is the difference between V1 and V2, the difference between the worst case outcome and the next best outcome. And this is the probability of getting that next best outcome with value V2 or a better outcome. So that's the probability of getting V2 or V3. And then R is again this mysterious risk function that I keep mentioning that weighs that probability. So it's a function of this probability in here, and it's going to allow us to weigh that probability lower, to give more weight to the worst case outcome, less weight to this next outcome, and even less weight to the next outcome after that. And then we're going to have these same few terms repeated for V3, for I equals 3. So the probability that the act ends up being at least as good as an outcome with value V3, multiplied by the difference between V3 and V2. Okay. So we can then just fill this in. It's going to be 1. V1 is 1. This probability is going to be 2/3. Because the probability of value 2 or higher is 2/3. So it's 2/3 times 2 minus 1. And then likewise for V3, probability of that much value or higher is 1/3 times 3 minus 2. And we apply this R function to each of those. Just as an example of an R function, we can suppose that R equals P squared. So it just takes the square of the probability. And surprisingly, that does actually reduce the amount of probability because probabilities are between 0 and 1. But anyway, this is just an example of a function that we could use. So getting rid of r of 2/3, and we write 2/3 squared instead, because that's our r function that we're using, and we'll square the 1/3 as well. And we end up with the number 1 5/9. So that's a bit less than 2, about 1.5. And notice that 1.5 is lower than the expected value of this bet. So the expected value here is the same as the average value, it's just 2. So expected value theory says this act is equally preferred to just having value 2 for sure. Risk-weighted expected utility theory is going to say, no, it's worse than that, it's less preferred. It's equally preferred to getting value 1 5/9 for sure, which is a little bit lower. So like an expected value, we're still taking kind of the average of these values, but we're giving more weight to the lower values, to the worse, less preferred outcomes, the worst case scenarios. And so we end up with a weighted average, giving more weight to the worst case. And so it's a bit lower. Okay. So again, scary equation. Hopefully it's slightly less scary now. And don't worry, you will get plenty of practice using this equation, and it will get less and less scary over time, I hope. But one thing you might wonder when trying to use this equation is, we keep using this r function. What on earth is that? What does that actually mean? What's r? Well, again, it's what Buchak calls the risk function, and it's going to represent whether we're risk averse or not. It's going to represent our attitude towards risk, whether that's the attitude of the decision maker or whether our intuitions about risky cases align with a particular risk attitude. Either way, this risk function represents some attitude to risk. And remember that under expected utility theory, we had a utility function u, and that would determine our preferences over acts. That would have to kind of represent and capture any risk attitude we have. And perhaps we can pin down a particular utility function u by some further arguments, perhaps by reflective equilibrium, perhaps just by the decision maker's own attitudes, whatever it might be. And if we want to capture risk aversion, if we want to capture an attitude towards risk that isn't just risk neutral, then it's got to be captured within the utility function. So the utility function serves that purpose for expected utility theory. Under this new theory, risk-weighted expected utility theory, we're going to have a risk function r as well. And that's going to serve the same purpose as a utility function. It's also going to represent risk attitudes. It's going to capture our preferences over acts, including our risk attitudes. So these general patterns of our preferences over risky acts. And like a utility function, we could determine the correct risk function r, perhaps by further arguments, or perhaps by reflective equilibrium, or perhaps just by the decision maker's own attitudes. It's kind of left open by the theory, just like the utility function u was left open by expected utility theory. But if we've got a risk-averse decision maker, then we can get a risk function r that might fit their preferences. Or if you, as someone doing reflective equilibrium, are risk-averse and your intuitions about what it's rational to do are a bit risk-averse, then that's fine because we can accommodate risk aversion within an r function. Now, a little more about this risk function r. If we were to draw it like we drew the utility function before, it would look like this. So remember, it's a function of probabilities. Probabilities go from 0 to 1. And since the r function is effectively replacing these probabilities with smaller probabilities, the r function is also going to go from 0 up to 1. And if you're risk averse, your r function is going to look like this. It's going to be convex. It's going to go up. It's going to get steeper and steeper. The higher the probability is already of getting such and such value, the more that additional probability is going to count for in terms of the r function. And yes, r of 0 must always start at 0, and r of 1 must always end at 1. Now, this is the shape of the graph if you're risk averse. If you are risk neutral, it would just be straight because you don't weight the probabilities any differently. You replace probability a half with probability a half. So the r function is just a straight line, and that's what it would be under expected utility theory. So you could think of expected utility theory as just risk-weighted expected utility theory with the r function a straight line. We can also capture risk-seeking preferences with this theory and with an r function that's a different shape. It would be concave. It would go the other way like that. That would give you risk-seeking preferences. But we'll be focusing on risk-averse preferences, perhaps because they're more plausible. Okay, and just as examples of R functions that kind of have this shape, R of p equals p squared is going to look roughly like this. R of p equals p to the power 3 is going to look like this, but it's going to go even lower before it starts going up. Effectively, this function, p to the power 3, is going to mean you're more risk-averse. And in fact, in this unit, I think all the risk functions we'll look at will just be of this kind of form. R of p equals p to some power, squared, cubed, whatever. Okay, it's time for the official definition. So here is a definition that you should recognize from before, expected utility theory, and we can make sense of risk-weighted expected utility theory as a kind of deviation from this. This with some slight changes. So the definition looks like this, with the changes in black. So risk-weighted expected utility theory says, again, we've got some utility function from the set of outcomes to the real numbers, and that represents preferences over outcomes. Just like before, that should be okay. We've also got this extra kind of moving part, this extra degree of freedom, this risk function R, and that's from the set of numbers from 0 up to 1, like all the possible probabilities, to the numbers from 0 to 1. So we're turning probabilities into slightly differently weighted probabilities, basically. And it's going to say then basically the same thing. For any acts A and B, A is weakly preferred to B if and only if the risk-weighted expected utility of A is at least as great as that of B. And we're going to define the risk-weighted expected utility of an act the way we had it before, a few slides ago. So same equation, except one difference. I've replaced V1 and VI and so on with utilities because, strictly speaking, REU theory can use both the risk function R and a utility function U to determine preferences. But to keep the number of moving parts kind of minimal, we will just focus on cases involving REU where the utility function matches the value function, so it's not too confusing. Okay. Now again, the differences between these two theories are, first of all, we have an extra function R, a risk function, which is going to help represent preferences. And second, we've got a new equation which uses this new function to take the kind of weighted average of the utilities of outcomes in a slightly different way. In a way that would be the same as the expected utility if we just didn't have this R function, this risk function. Okay, so again, same definition, I've just moved it up here. And again, yeah, if R is linear in probability, or just R of p equals p, then REU theory just says the same thing as expected utility theory. So I get to use this meme again. These are the same picture. Expected utility theory, REU theory with R of p equals p. And as a result of that, if R is linear in probability and also U is linear in value, then REU theory says the same thing as expected value theory. Since it says the same thing as expected utility theory, and expected utility theory then says the same thing as expected value theory. Also perhaps worth being aware of, REU theory sometimes goes by different names, especially in economics, so it's equivalent to what economists call rank-dependent utility theories, and also more specifically anticipated utility theory. But these aren't terms that we need to worry about here, it's just for any PPE students who come across this in their economics courses. Okay. And like expected utility theory, Buchak has her own representation theorem for this theory, with its own set of axioms, which then imply that this theory has to hold. But those axioms are quite complicated, the proof is also quite complicated, and we don't have to worry about it here. So it's okay, don't worry. And here's a task for you. I want you to use this equation here, take it out for a spin, and try and find the REU, the risk-weighted expected utility, of risky bet here, and of safe bet. And if you want to, you can pause and go back a few slides and have a look at the steps we gave of, first find V1, then find V2, V3, etc., and then find such and such probabilities. You can follow those steps if you like, or you can just try and fill out this equation directly. And for the sake of simplicity, here you can suppose that the utility function U is just linear in number of lives saved, keeping it simple, and also pick the risk function R of p equals p squared. It's a pretty simple one to use. I'll give you a little while to try and calculate that. But yeah, feel free to pause and actually take as much time as you need if you want to. Okay, time's up. If you had absolutely no trouble with this, feel free to fast forward the next little bit. But in case you did have any trouble, here's how I would do it. So here's our equation, and here's our case. First, let's look at risky bet. And first, looking at risky bet, we take the utility of each outcome. The utility of this is just 2. The utility of 0 lives saved is just 0. Given that utility is linear in number of lives saved. Then we're going to list these outcomes from worst to best, which the worst utility, the lowest utility U1, that's 0. The highest is U2 equals 2. Now, what's the probability of at least this much utility? So only starting from U2 and above. For V1, we don't care about the probability. Starting with U2, what's the probability of at least that much? Well, it's just a half. And now we have everything we need to fill this in. And again, do watch out in other cases where we have more than 2 outcomes, that this isn't always just the probability of the outcome. Rather, this is going to be the probability of that outcome or an outcome that's even more preferred. So here it's a half, but remember in the case with the 3 outcomes, with the roll of the die, and each had a probability a third, that there, this probability became 2/3, because it's not just the probability of the outcome. It's probability of that outcome or something even better. Okay. So this is all we need to fill in the equation. And it ends up saying 0, which was U1, 0 plus R of 1/2, since that's a probability, times 2 minus 0, which is U2 minus U1. And we only have one term like this to add up because U2 is the highest utility. So it goes from I equals 2 to N equals 2. We're not adding up that many terms. So it's just this, and it becomes 1/2. 1/2 squared times 2 is equal to a half. Okay, so the REU of risky bet is then 1/2. What is it for safe bet? Well, that's very simple. The utility of each of its outcomes is just 1. List them from best to worst. Well, U1 equals 1, that's all we've got. And then for U2 and above, what's the probability of at least that much utility? Well, there is no U2 or above, so we don't have to worry about that. So the equation just says the REU of safe bet equals 1, because there are no terms like this to add up, so we just have to worry about U1. Okay. So 1, of course, is higher than a half, so this is higher than the REU of risky bet. So expected utility theory would then say that safe bet is strictly preferred to risky bet. And if you yourself are risk averse, you might agree with that. You might think, yeah, that seems like the right verdict, because risky bet is just so much riskier. We want to say that its instrumental value is a bit lower than 1, a bit lower than the instrumental value, and in fact, the actual value of safe bet. Okay. So as you can see, despite this equation maybe looking a bit intimidating, really just going step by step, none of the steps is especially complicated, especially once you've got some practice with it. Now, that's the theory and how we might apply it, at least in a simple case. what does the theory imply about other sorts of cases we might care about? Now, go back to the Allais paradox, in which you might have these preferences in these two cases. So you might prefer $100 million for sure, but you might also prefer having this chance at 500 million over this slightly higher chance of 100 million. And remember that these preferences together violate independence. Well, RAU theory can give both verdicts. In fact, with the same R function and U function. So RAU theory makes these verdicts consistent. It doesn't rule them out, having them together. So in effect, RAU theory can violate independence. And you might think this is a good thing about the theory, or you might think it's a bad thing about the theory. So you might think it's good because you might have intuitions in this case that say, yeah, this one's strictly preferred, and also this one's strictly preferred over that one. And you want to uphold those intuitions as rational. You want your theory to be able to accommodate them. And RAU theory can do that, so maybe that's good. But on the other side, you might, from last week, have found independence really intuitive. You might have really thought it was a no-brainer. It's kind of like statewise dominance, but now with kind of acts rather than states. And statewise dominance was super, super plausible, I think, personally. Another reason to think that independence is pretty plausible is this. So note that if any of these states happen, none of the other states can happen. So either this one happens, or this one happens, or this one happens. And likewise, either this state happens, or it doesn't happen, and we're facing acts like these. So either this happens, and the acts are just exactly the same, who cares what you chose, or it doesn't happen, and conditional on it not happening, you're facing this act, ignore that, facing this act or this act. And then it seems rational to just evaluate these two acts based on your preferences between this smaller act and this smaller act. So given that we know either this will happen or it's not going to happen and we can condition in this way, and either way, either there's no difference between the acts or we would prefer one thing or the other, it seems plausibly rational that we should just compare the acts overall in the same way. Given that if one state happens, the other states don't happen. It's a bit odd that what's happening in this state could influence how we value these states here, or the act that is made up of these just a couple of states. It seems kind of weird that what happens over there could influence the value of what's happening over here, the instrumental value, that is, when it doesn't in fact happen. That's kind of strange. Okay, so RAU theory can violate independence. Is this good or bad? Well, there are different positions you can take on this. One comes from your reading last week from John Broome, who looks like this, and he says this. So in the case before, we had numbers being drawn. In that case, either one number or another must come up. If one comes up, the others cannot. And the value you assign to what happens in one state of nature should depend on what it will be like if that state occurs. And by value here, he means kind of instrumental value of having that state on the table, that kind of possibility of an outcome. But if that state occurs, no other state does. So what would have happened in the other states should make no difference to the instrumental value that we assign to what may happen in that state. For a rational person, he suggests, there should be no complementarity. There should be no kind of interaction between what happens in these different states. He asks, how can something that never happens possibly affect the value of something that does happen? So if one state happens, the other does not. And nonetheless, if we're violating independence, it seems that we're letting some outcomes affect how we evaluate other outcomes, even when those outcomes don't occur. Seems a little weird, he reckons. So the instrumental value of having a 1/2 probability of some outcome, or as in your instrumental reasons in favor of having such and such probability, he reckons that mustn't depend on the other outcomes and their probabilities. That's one line of thinking, a very common line of thinking in decision theory, and upheld by everyone who likes expected utility theory. And then here's Lara Buchak, and she thinks, no, independence is wrong. It's fine if there's this kind of complementarity, if the instrumental value of having 1/2 probability of some outcome depends on the other outcomes, what happens the other half of the time. So it seems rational to care about whether an outcome in one state is specifically the worst case outcome of that act. Seems like that can matter rationally. And if it's rational to care about that, doing so involves such complementarity. The instrumental value of having a 1/2 probability of some outcome becomes dependent on what the other outcomes are. Because whether that outcome is the worst case outcome depends on what the other outcomes are. Or you can think of what she's saying as basically the preferences in the Allais paradox seem rational. It seems rational there for the instrumental value attributed to having such and such outcome in such and such state. It seems rational for that to depend on what the act looks like as a whole. And if so, then independence must be false. Independence seems false because those preferences seem rational. Effectively, because it seems fine for the instrumental value of a particular outcome in a particular state to depend on what the act looks like as a whole. So here we have either an argument for REU theory rather than expected utility theory, or we have an argument against it. If you like independence and you kind of agree with Broom's line of reasoning, then we have an objection. REU theory violates independence, therefore it must be false, whereas expected utility theory may well be true. On the other hand, if you disagree with this line of reasoning, and or you think those preferences in the Allais paradox seemed perfectly rational, then you have an argument in favor of REU theory compared to expected utility theory. You should dismiss expected utility theory and adopt this theory or perhaps something else. So depending on what you think about this, you may or may not like REU theory. Okay, here's another argument specifically against REU theory, which we've already seen a more general version of in a previous week, and it's the background uncertainty argument. So recall the version that we saw that was general and was an argument for expected value theory. So take any acts A and B where A has higher expected value. So for instance, here's a case, a risky bet for 3 lives versus a safe bet for 1 life. And this first one has higher expected value. Okay, fine. And also we're going to assume that stochastic dominance is true. Well, Christian Tarsney had this result, the details of which don't really need to concern us, but mathematically we can always come up with some risky background events such that A, this first act, risky bet for 3 lives, with those risky background events going on, is strictly preferred to the second one, safe bet, with those risky background events going on, at least by stochastic dominance. So, if we want our verdicts, our preferences over acts, to be consistent, whether or not there are risky background events happening in the background, you have to accept expected value theory, or else reject stochastic dominance. And as a result, reject REU theory, at least REU theory with any nonlinear risk or utility function. So that's the version we saw in a previous week. We can also look at a version of this specific to REU theory, specifically against REU theory. So again, consider these 2 acts. And let's suppose that our risk function is just p squared, r of p equals p squared, and our utility function is linear in lives saved. So u of x equals x, where x is number of lives saved. Well then, REU theory says that safe bet is strictly preferred. It has higher REU than risky bet for 3, as I think we saw before. Now, consider what happens if your uncertainty here is not so simple. So we introduce a risky background event, which we can just make someone else taking that same act, risky bet for 3 lives, over somewhere else. Well then, the decision matrix looks like this. So still, we have 2 acts, risky bet for 3 lives with something else happening in the background, and safe bet with something happening in the background. But now we have 4 states to account for that extra uncertainty about what's happening over in the background with someone else taking this act as well. So first state, your coin lands heads, their coin lands heads. Second state, your coin lands heads, theirs lands tails, and so on. And the number of lives that then get saved in each outcome, it's the sum of the number of lives that are saved directly by your action and the number of lives that are saved by this other person's action, with them also taking the bet. So it becomes 6, 3, 3, 0, and so on. Okay. Now, with this new pair of acts involving some risky background event going on, what's the REU, the risk-weighted expected utility of each of these new acts? Well, for this one, risky bet for 3 lives with other stuff going on, it becomes just filling in the equation quickly, you can go and fill it out yourself and check that this is correct if you would like. It becomes 0 plus 3/4 squared times 3, etc., blah, blah, blah. It becomes 1 and 7/8. So it's almost 2, which you might notice is a lot lower than the expected value, the expected utility of this act. Okay, and for safe bet with background stuff going on, it becomes 1 3/4, which is still just lower than 2, but it's slightly lower than the REU of the first thing. So REU theory with that risk function and that utility function, it says that this first act is strictly preferred, which, remember, is different. Before, when there was no background stuff going on, the REU of safe bet was higher. REU theory said safe bet was preferred. But now that we've got background stuff, it's saying that the risky bet is strictly preferred. The verdict changed. And this actually happens in general. You can prove this. If you have any nonlinear risk function R or any nonlinear utility function U as well, either of those will result in some cases where this will happen, where the REU, where the ranking of acts in terms of their REU will change. Okay, so here is how we might kind of state the argument, premise by premise. So verdicts, like safe bet being preferred to risky bet, must be consistent no matter what risky background events we introduce. And you might think that generally this is plausible. The kind of example that I like for this that illustrates it nicely is, suppose we're making moral decisions and we care how many people have happy lives. We want more people to be happy, or we might care about other stuff, but nonetheless, we care about how other people's lives go. And for any moral decision you're making now, presumably you're only going to affect people now and in the future. So you're comparing two acts and they might be different levels of risk, whatever they are. But really, how good the world overall turns out morally, that's kind of from the beginning of time to the end of time, how good was that? Well, that depends not only on the effects of your actions, but on a whole bunch of stuff that you're uncertain about. So I'm a philosopher, not an Egyptologist. I don't know almost anything about history, so I'm very uncertain about how good people's lives were in ancient Egypt. There's a big old risky background event happening there of, how much moral value there was in ancient Egypt. And likewise, lots of things about the world that I just don't know about. And in my decisions, the acts I'm choosing between, I'm not causally affecting what happened in ancient Egypt. But nonetheless, if I adopt a decision theory like REU theory that makes the correct verdict depend on what risky background events there are, such as, for instance, what happened in ancient Egypt, of which I'm uncertain, then the correct acts for me to take now, what I'm required to do instrumentally, depends on what I believe about ancient Egypt, what happened there, and also my uncertainty about what happened there. And you might think that's kind of silly. You might think, in general, no, our verdicts must be consistent no matter what risky background events we introduce, no matter what I believe about what happened in ancient Egypt. Okay, that might seem pretty plausible, especially in the moral case. So, premise one. Second, REU theory with any nonlinear risk or utility function won't always be consistent. In this sense, REU theory will always be inconsistent, at least a little bit. We've demonstrated it for one R function and U function. You can also prove it for other R and U functions. Therefore, REU theory must be false, at least if we have nonlinear R or U function. Okay, so that's a background uncertainty argument against REU theory. We basically, to follow REU theory, we need to accept that risky stuff going on in the background that can change what we're required to do if those things going on in the background are things that we actually care about in our value function. Okay, so now to sum up points for and against this new theory. An advantage of REU theory, you might think, is that it can give the intuitive preferences in the Allais paradox. But then a disadvantage you might see, you may or may not consider this a disadvantage, REU theory violates independence. As well, REU theory can give the intuitive preferences in the Hansen case, where we're kind of adding value 100 to all the outcomes, or we're scaling up the outcomes, multiplying by 10, that sort of thing. And likewise, REU theory can give a whole lot of other preferences that you may or may not think are intuitive. It's just far more capacious. It's far more welcoming to a variety of preferences. So you might think that's an advantage. But then on the other side, we have a background uncertainty argument against it. So the verdicts of REU theory, because they deviate from expected value theory, they won't be consistent over different risky background events. And likewise, we can also run a long-run argument against it, because long-run arguments lead to expected value theory, and so against REU theory. Verdicts of REU theory won't be consistent over many independent repetitions of the same acts. And I'll leave it for you to decide whether the pros or the cons come out in front, whether this is REU theory over here, or whether this is REU theory over here, and meanwhile, expected utility theory or expected value theory is the one on the other side. I'll leave that up to you. And for the lecture this week, we can leave it there. I look forward to seeing you all on Friday. Thanks.